In Chapter 4, Section 4, we'll be reviewing counting methods. In this section, we'll be introduced to 5 methods of counting, including the multiplication rule, factorial rule, the permutation rule, and combination. This section requires much greater use of formulas as we consider 5 different methods for counting the numbers of possible outcomes in a variety of situations. Not all counting problems can be solved with these 5 methods, but they do provide a strong foundation for the most common real applications. For a sequence of events in which the first event can occur in n1 ways, the second event can occur in n2 ways, and the third event can occur in n3 ways, and so on and so on and so on, the total number of outcomes is n1 times n2 times n3 and so on and so on and so on. This is the multiplication counting rule. Let's consider this example. A fast food restaurant has a meal special. For $5 you get a drink, a sandwich, a side item, and a dessert. And your choices are as follows. For the sandwich, you can choose from a grilled chicken or all beef patty, veggie burger, or a fish fillet. Your side items, you can choose from regular fries, cheese fries, or potato wedges. Your desserts, you have a choice of a chocolate chip cookie or an apple pie. And for your drink, you have your choice of Fanta, Dr. Pepper, Coke, Diet Coke, and Sprite. So the question is, how many possible meal combos are there? Well, there's 4 stages here. You choose a sandwich, you choose a side, you choose a dessert, and then you choose a drink. So there are 4 different types of sandwiches, 3 different types of sides, 2 different types of desserts, and 5 different types of drinks. So the possible number of meal combos is 4 times 3 times 2 times 5 equals to 120. There are 120 possible meal combos for this restaurant special. Let's consider another example of the multiplication rule. This one is a hacker guessing a passcode. When making random guesses for an unknown 4-digit passcode, each digit can be between the values of 0 to 9. What is the total number of different possible passcodes? Given that all of the guesses have the same chance of being correct, what is the probability of guessing the correct passcode on the first attempt? Recall that each digit can be any number between 0 through 9. So there are 10 different possibilities for each digit, so that the total number of different possible passcodes is equal to n1 multiplied by n2 multiplied by n3 multiplied by n4, which is equal to 10 times 10 times 10 times 10, which is equal to 10,000. Because all of the passcodes are equally likely to occur, the probability of getting the correct passcode on the first attempt is 1 out of 10,000, which is equal to 0.0001. The number of different arrangements where order matters of n different items when all n of them are selected is known as a factorial and is denoted as n exclamation point. Let's review the notation for the factorial rule. The factorial symbol, the exclamation point, denotes the product of decreasing positive whole numbers. A special definition of the factorial rule is that 0 exclamation point is equal to 1. The factorial rule is based on the principle that the first item may be selected in n different ways, and the second item may be selected in n-1 different ways, and the third item selected in n-2 different ways, and so on and so on. This rule is really the multiplication counting rule modified for the elimination of one item on each selection. Factorials are products of every whole number from 1 to n. For example, if n equals to 3, then 3 factorial is equal to 3 times 2 times 1 equals to 6. If n equals 5, then 5 factorial is equal to 5 times 4 times 3 times 2 times 1 equals to 120. It's a shorthand way of writing numbers. For example, instead of writing 479 million and 1,600, you could write 12 factorial instead. Let's consider this example of the factorial rule. A statistics researcher must personally visit the presidents of the Gallup, Nielsen, Harris, Pew, and Zogby polling companies. How many different travel itineraries are possible? And if the itinerary is randomly selected, what is the probability that the presidents are visited in the order from youngest to oldest? Let's find the solution for part A. For those 5 different presidents, the number of different travel itineraries is 5 factorial. That's because there's 5 different presidents to choose from for the first visit, and then there would be 4 remaining for the second visit, and then 3 remaining for the third visit, 2 remaining for the fourth visit, and 1 remaining for the last visit. So 5 factorial equals to 120 different travel itineraries. Note that this solution could have been done by applying the multiplication counting rule. The first person can be any one of the 5 presidents, the second person can be any one of the 4 remaining presidents, and so on. The result again is 5 times 4 times 3 times 2 times 1. Recall for part B, we want to solve the question, if the itinerary is randomly selected, what is the probability that the presidents are visited in order from youngest to oldest? Well, there's only one itinerary with the presidents visited in order of the age, so this probability is simply 1 over 120. Permutations of items are arrangements in which different sequences of the same items are counted separately. For example, the letter arrangements of A, B, and C can be ABC, ACB, BAC, BCA, CAB, and CBA. And these are all counted separately as 6 different permutations of those letters. Combinations of items are arrangements in which different sequences of the same item are counted as being the same. So, for example, the letter arrangements of ABC, ACB, BAC, BCA, CAB, and CBA are all considered to be the same combination. The hardest part about solving permutations and combination problems is this: which one is a combination and which one is a permutation? For combinations, if you don't care about the order of things, it's a combination. So if you think about combining ingredients, flour, salt, and water mixed in a bowl would be the same as salt, water, flour. With permutations, if you do care about order, then it's a permutation. For example, picking winners for the first, second, and third place raffle would be a permutation because in that case, order does matter. Here are a couple of mnemonics that may help you remember the difference between permutations and combinations. If you remember permutations position, where the alliteration reminds us that with permutations, the position of the item makes a difference. You could also remember combinations committee, which reminds us that with members of a committee, arrangements and rearrangements of the same members result in the same committee, and so order does not matter. Here's the permutation rule. When we have n different items that are available, and there are of them that are selected without replacement. The number of different permutations is given by n factorial over n minus r factorial. Let's consider this example for the permutation rule. In a horse race, a trifecta bet is won by correctly selecting the horses that finish first, and then second, and then third. And you must select them in the correct order. The 140th running of the Kentucky Derby has a field of 19 horses. Let's find the solution to these two questions for our example. First, how many different trifecta bets are possible? And second, if a bettor randomly selects 3 of the horses for a trifecta bet, what is the probability of winning by selecting California Chrome to win, Commanding Curve to finish second, and Danza to finish third? Do all of the different possible trifecta bets have the same chance of winning? The solution for part A is that our n equals to the 19 horses available, and we must select r equals to 3 of them without replacement. So the number of different sequences of arrangements can be found as n factorial over n minus r factorial, which is equal to 19 factorial over 19 minus 3 factorial, or 19 factorial over 16 factorial. And this gives us 5,814 possible combinations. There are 5,814 different possible arrangements of 3 horses selected from the 19 horses that are available. If one of those arrangements is randomly selected, there would be a probability of 1 over 5,814 that the winning arrangement is selected if all of the horses have the same chance of winning. So there are 5,814 different possible trifecta bets, but not all of them have the same chance of winning because some horses tend to be faster than others. Note, we have 2 different ways to consider the permutation rule. The first is when all of the items are different. The second way we can look at the permutation rule is when some of the items are identical to each other. Let's consider the permutation rule when some of the items are identical to others. So we say the number of different permutations when n items are available and all n of them are selected without replacement, but some of the items are identical to others, is found as follows: n factorial over n1 factorial multiplied by n2 factorial, and so on to nk factorial, where n1 are all alike, n2 are all alike, and nk are all alike. Let's consider this example of designing a survey using the permutation rule with some identical items. When designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one particular survey with 10 questions, 2 of the questions are identical to each other, and 3 other questions are also identical to each other. For this survey, how many different arrangements are possible? Is it practical to survey enough subjects so that every different possible arrangement is used? So for our survey, we have 10 questions with 2 that are identical to each other and 3 others that are also identical to each other. And we want the number of permutations. Using the rule of permutations with some items identical to others, we get n factorial over n to the 1 factorial times n to the 2 factorial. This is equal to 10 factorial over 2 factorial times 3 factorial. And that gives us a total of 302,400 different permutations. So we can interpret these results as follows. There are 302,400 different possible arrangements of the 10 questions. It is not practical to accommodate every possible permutation, because for a typical survey, the number of respondents is somewhere around 1,000. Now let's consider the combination rule of counting. When n different items are available, but only r of them are selected without replacement, the number of different combinations is found as follows. The combinations are n factorial over n minus r factorial multiplied by r factorial. Let's consider this example. In California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 to 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order doesn't make any difference. So let's answer the questions: how many different unique lottery tickets are possible? And let's find the probability of winning the jackpot when one ticket is purchased. Let's solve part A. There are n equal to 39 different numbers available, and we must select r equal to 5 of them without replacement. This is because each selected number must be different from the other selected numbers. Because order doesn't matter, we need to find the number of different possible combinations. We get this as n factorial over n minus r factorial multiplied by r factorial. That gives us 39 factorial over 39 minus 5 factorial multiplied by 5 factorial, and that gives us 575,757 different combinations. Recall for part B, we want to find the probability of winning the jackpot when one ticket is purchased. The solution for this is, if you select one 5-number combination, your probability of winning is 1 over 575,757. Typical lotteries rely on the fact that people rarely know the value of this probability and have no realistic sense for how small the probability of winning really is. This is why the lottery is often called the tax on the people who are bad at math. This is the end of Chapter 4, Section 4. Your module for these two sections is posted on our Canvas site, and the homework is also posted in there.